we mentioned that the support vectors are the points that is closest to the decision boundary or the margin. So here, what this regularization parameter is trying to penalize is the points that is out of the margin. So say, for example, the point that it is trying to penalize here, it's the nearest data point of this margin. So say, for example, this is the margin for the blue class. So now what it is trying to penalize here, it's the point that happens or appear in the opposite side of the margin. And this, and for this margin, the margin of the red color classes, they are trying to penalize the dot which is on the opposite side. This is how SVM regularizes and therefore prevents it from overfitting. So how do we fine-tune this parameter C? This C is a parameter for us to fine-tune if we were to train a support vector machine. So if we were to include, we can see that C is a indirect proportional function to this cost function. Therefore, with a higher C value, it will result in a smaller margin, but it will also allow this classifier to make less mistake. So with a lower C value, what it results in is a larger margin. What it means to us is that we are allowing the classifier to make more mistake on the training data set. So now this regularization parameter C is one of the very important parameter to fine-tune if you are training a SVM model. So that's the first thing to optimize if you are training a SVM model. And there are more to come in terms of training this SVM because it is a very advanced model. And we shall come to what you should need to tune in the later stage. So as a summary of what we just talked about, so SVM is a non-linear models that help us to maximize the margin between classes using support vectors only. The important points that separates between the two classes, the borderline dots. So the cost function of this SVM is the hinge loss function, which penalize the misclassification to encourage larger margin. So regularization will then penalize complex hyperplane to prevent this model from overfitting to our training data. Okay, so before we move on, any question? No? Am I clear? So, okay. So the next part that we want to talk about regarding this SVM is this SVM can be linear and can be non-linear. And what decides this SVM to be linear or non-linear is the kernels. And we will talk more about kernels in the later stage. So for those who are doing CV and NLP at the same time, this kernel is different from the other kernel that we have discussed in the convolution neural network. Okay, so this kernel is referring to a kernel trick. So this kernel is the thing that allows this SVM to make or to produce non-linear decision boundaries. So in machine learning, not deep learning, this kernel is usually referred to a kernel trick, a method that is used for this linear classifier to resolve a non-linear problem. So we are going to look at some very interesting concept over here that is regarding this kernel. So it is a function that takes two data points as input and returns a similarity score between them. So let's take a look at an example. So now, we know that in real life, not all of the classes, they are linearly separable. In certain times, we may come to realize that there are certain tasks or items which are embedded among other classes. So in this case, if we were to draw a decision boundary to separate between these two classes in this distribution, it's almost pretty hard for us to draw a clear line. So in order to separate between the two classes, we have to draw a circle. So now, how does this SVM able to use a straight line or a straight plane to separate these two classes is by a trick called kernel trick. So what it is trying to do here is, why don't we raise these data points up to another dimension? So then, if you were to raise the pink color points above to another dimension, we can then cut this off using a hyperplane. So now this is what is meant by a kernel trick, okay? So what we are trying to do here is, say for example, we were to lay every single point on a flat surface. All of them exist in a 2D dimension. What this kernel trick does is that it is trying to raise the pink color point up to another level, to the third dimension, and then cut it off with a decision surface or a hyperplane using this kernel trick, okay? And this is called the kernel. So kernel can be used to map the data to a higher dimensional space where it is more likely to become linearly separable. So now the point is, we are trying to turn drawing a circle line we are moving away from drawing a circle line to drawing a flat surface across these two non-linearly separable classes. Okay, you understand that? It is not very hard to understand. Yeah, so that's something simple. So then let's take a look at another example of what we meant so far. So just imagine that we have data in two-dimensional space. So these are the two classes which we are trying to separate. And this kind of pattern of classes usually happens in our real-world data. Yeah. So what happens here is that we will often come across a lot of instances where the class that we are trying to separate out from the rest actually are embedded among other classes. So what we can do using this kernel trick is then we are turning these two sets of data, these two classes of data, using a third dimension. So once we raise a certain class of these instances into a higher dimension, we can then create a linear line that separates between the two classes. Okay. So you get the point of how smart this SVM is about, and how smart are the scientists who came out with this idea, right? Okay, so how do we do that is ultimately, that was at one of the point, this is one of the largest research area ever. So what the researchers are trying to figure out is, how can we transform these data points using some kernel functions to raise them into another hyperplane. So these functions that are being developed are called the kernel functions. So ultimately, this kernel function tries to figure out is, it tries to transform the training set of data into a higher dimensional space. And there are many methods of them, and three of the most commonly used one are the linear kernel function, polynomial kernel function, and radial basis kernel function. Okay, so in the case where you are training a support vector machine, it is important to find out the most optimized regularization parameter C, as well as to find out what is the best kernel function that describe or would separate your classes most effectively. Okay, so there are some of the guidelines to choose this kernel function, but ultimately we will be testing it out using a trial and error method between linear, polynomial, and radial basis function. So the time that it takes to for this SVM to learn, in an increasing order is linear, polynomial, and radial basis function. And the ability to fit to any data is also increasing in this manner, where the lowest ability will be the linear one, because it's the simplest, polynomial followed by radial basis function. So in terms of reducing the overfitting risk, the risk of overfitting, we can also see that they rank in the same manner. Whereas for underfitting, it is just the opposite way, so they are ranked in descending order. In terms of numbers of hyperparameter that we are trying to find out or trying to tune, linear kernel functions, we have non-hyperparameters to tune. Radial basis function, we have 2. And polynomial, we have 3 hyperparameters to fine-tune. Okay? So what are the hyperparameters that lies behind this kernel function is something that you can refer to the scikit-learn package and refer to the support vector machines document. Okay? So what we just discussed are the kernel trick that comes along with these support vector machines. So these kernel tricks, it's the one that allow SVM to create non-linear decision boundaries by raising our data points between different classes into a higher dimensional space. So some of the most popular kernel that helps us to raise this data point into a different dimensional space are linear kernel, polynomial kernel, as well as the radial basis kernel. Okay. Questions? No? That's the end of our class today. So next week is your holiday. So just a reminder, those who have not completed your midterm test, please complete it by this Sunday. And if you need more time, don't feel shy to reach out to me. And for those who are having practical class, would you like to stay here or go to the lab? Staying here? Okay, so we can stay here. And happy holiday, everyone. What is intuition in SVM intuition? Intuition is a way of how these support vector machines makes a decision. So we talk about logistic regression. In logistic regression, it is leveraging on the beta and beta naught and beta 1. So ultimately, the intuition of logistic regression is based on probability. Whereas for these support vector machines, the intuition is on minimizing the misclassification as well as maximizing the margin between our decision boundary and its support vector. Okay?